Hello, in this lecture we will find the radius of the small circle. In the drawing we have square ABCD. We know that one side of this square equals to 8 units. We also know that inside this square ABCD we have two circles. The radius of this big circle is 2r and the radius of this small circle is r, and we want to find out the value of r, or the size of the radius of this small circle. Okay, so before we solve the question, I will present to you two new rules. Rule number 1 states that a tangent to a circle is perpendicular to the radius drawn to its point of tangency. I will read rule number 1 again. Rule number 1 states that a tangent to a circle is perpendicular to the radius drawn to its point of tangency. So what is the meaning of rule number 1? Rule number 1 states that if you have this circle and suppose that the center of this circle is here at point O, and we have tangent to this circle. Actually, here tangent AB is tangent to this circle at this point M, and if we have radius of this circle that is drawn to the point of tangency, that is to say point M, okay, actually this radius is drawn to the point of tangency. The point of tangency is point M, and this radius is drawn to the point of tangency. Therefore, according to rule number 1, the tangent AB is perpendicular to this radius that is drawn to its point of tangency, that is to say to point M. Therefore, the tangent AB is perpendicular to this radius, that is to say this angle equals to 90 degrees, and this angle also equals to 90 degrees. So according to rule number 1, whenever you have radius that is drawn to the point of tangency of a tangent, then the tangent will be perpendicular to this radius, that is to say this angle will be equal to 90 degrees and this angle will be equal to 90 degrees. Okay? So that was rule number 1. I will present to you also rule number 2. rule number 2 states that if from one external point two tangents are drawn to a circle, then they have equal lengths. I'll read rule number 2 again. Rule number 2 states that if from one external point two tangents are drawn to a circle, then they have equal lengths. So what is the meaning of rule number 2? The meaning of rule number 2 is that if you have circle and from an external point of this circle, that is to say this point P is an external point in relation to this circle because of the fact that point P is neither inside this circle, neither on this circle, but is outside of this circle. Therefore, point P is defined as external point in relation to this circle. And so if from point P we draw two tangents to this circle, then the first tangent we will define the touching point between this tangent to the circle as point A, and we will draw also second tangent from point P to this circle. So this is the second tangent to this circle. We will define the touching point between the second tangent to this circle as point B. So according to rule number 2, the lengths of those two tangents are equal to each other. That is to say, PA equals to PB. So whenever you draw two tangents to a circle from an external point, then the lengths of those two tangents will be equal to each other. That is to say, in this case, PA equals to PB. Okay, so that is actually rule number 2. And in the next step, we will define the center of this small circle as point P, and the center of this big circle will be defined as point Q, and we will join together points P and A by a straight line. Then we will define the touching point between tangent AB and this small circle as point M. Then we will join together points P and M by a straight line. PM is the radius of this small circle because of the fact that line segment PM starts from the center of this circle, that is to say from point P, and ends at point M, that is a point on the circle itself. Therefore, PM is the radius of this small circle, so it equals to R. And according to rule number 1, this radius PM is drawn to the point of tangency, that is to say to point M. Therefore, the tangent AB is perpendicular to this radius, that is to say this angle equals to 90 degrees, and this angle also equals to 90 degrees. Okay? We will define the touching, we will define this point as point E, and we will define the touching point between tangent AE to the small circle as point N. Then we will join together points P and N by a straight line. So actually Pn is the radius of this small circle. It equals to R because of the fact that line segment Pn starts from the center of this circle, that is to say from point P, and ends at point N, that is a point on the circle itself. Therefore Pn is the radius of this circle, and according to rule number 1, this radius Pn is drawn to the point of tangency, that is to say to point N. Therefore, the tangent AE is perpendicular to this radius, that is to say this angle equals to 90 degrees, and this angle also equals to 90 degrees. Okay? And we will define the touching point between tangent BC and the small circle as point L, and this radius PL is drawn to the point of tangency, that is to say to point N. Therefore, according to rule number 1, the tangent BC is perpendicular to this radius, that is to say this angle equals to 90 degrees, and this angle also equals to 90 degrees. And we also know that all 4 angles of a square are right angles. Therefore, angle ABC, that is 1 out of 4 angles of square ABCD, will be equal to 90 degrees. So this angle also equals to 90 degrees. It is a right angle. And so actually we will focus on quadrilateral PLMB. Okay, so on quadrilateral PLMB, we have three right angles, 1, 2, and 3. And the sum of three right angles is 90 times 3 is 270 degrees. And we have the rule that the sum of angles in any quadrilateral equals to 360 degrees. That is to say, the sum of those four angles, that is to say, the sum of these three angles plus the size of this fourth angle that will be defined as angle Z must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral equals to 360 degrees. Okay? Again, I'll repeat again. The sum of the three angles of quadrilateral PLMB plus the size of the fourth angle must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral equals to 360 degrees. We will subtract 270 degrees from this equality, and we will get that angle Z equals to 360 degrees minus 270 degrees is 90 degrees. So we found out that the size of this angle is 90 degrees. It is a right angle. So this angle is a right angle. It equals to 90 degrees. So because of the fact that quadrilateral PLMB has four right angles, it must be at least a rectangle. If not a square, it must be at least rectangle. Okay, so, and in rectangle PLMB, we have the rule that the opposite sides of a rectangle are equal to each other. So in rectangle PLMB, this rectangle PL will be equal to MB, because there are two opposite sides of this rectangle. So PL equals to MB, PL equals to MB. But we know that PL equals to R. We know that PL equals to R. So from this equality, we will conclude that MB also equals to R. MB equals to R. And we also know that PM equals to LB, because those two sides are opposite sides in rectangle PLMB, therefore they are equal to each other. PL equals to MB. But we know that PM equals to MB, to LB. PM equals to LB. But we know that PM equals to R, it is the radius of the small circle. So actually, from this equality, we will conclude that LB also equals to R. LB equals to R. So actually, a quadrilateral PLMB is a square, because it has 4 right angles, and all of its sides are equal to each other. They are all equal to R, so it is a square. Okay, and what is the size of side AM? The size of side AM, it is actually AB minus MB. Again, AB minus MB equals to AM. So I write it down. AB minus MB. AB minus MB equals to AM. Okay, again, AM equals to AB minus MB, but we know that AB equals to 8 units. 8 units, it is given us in the question. AB equals to 8 units, and MB equals to R. So in total we got that AM equals to 8 minus R. So we can write here that AM equals to 8 minus R. Okay? So in the next step, we will prove that those two right triangles congruent to each other. Okay? So we will prove that the right triangle APM, this right triangle, is congruent this is the sign of congruent, so the right triangle APM is congruent to the right triangle APN. Okay, APN. I will repeat again. We will prove that the right triangle APM is congruent to the right triangle APN. First of all, we know that AM equals to AN. Side AM equals to side AN. So why AM equals to AN? This is according to rule number 2. According to rule number 2, if you have external point A, and from external point A you draw two tangents to this small circle, then the lengths of those two tangents are equal to each other. That is to say, AM equals to AN. So AM equals to AN according to rule number 2. And we also know that PM equals to PN equals to the radius of this small circle. PM equals to PN equals to the radius of the small circle, and okay, PM equals to PN equals to the radius of this small circle. And we also know that PA is a common side, it belongs to both triangles, so PA equals to PA is a common side that belongs to both triangles. Common side that belongs to both triangles. Okay, PA equals to PA. It's a common side. So we actually proved that all three sides of the right triangle APM are correspondingly equal to all the three sides of the right triangle APN. Therefore, triangle APM congruent to triangle APN according to side rule. Okay, I'll write it down. triangle APM congruent. Again, this is the sign of congruent to triangle APN. According to side rule. So what is side rule? Side rule is that if you prove that three sides of one triangle are correspondingly equal to three sides of another triangle, then you proved actually that those two triangles can go into each other according to side rule. Okay? So from the fact that those two right triangles can go into each other, we will conclude that angle PAM, this angle, is equal to angle PAN, this angle. Those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding angles will be equal to each other. So actually angle PAM equals to angle PAN angle PAM equals to angle PAN according to the rule that corresponding angles in congruent triangles are equal to each other. And if we define angle PAN, this angle, as angle alpha, then angle PAN will be also equal to alpha because of the fact that those two angles are equal to each other. So we actually found out that angle PAM is equal to angle PAN, and both angles are equal to alpha according to our definition. Okay? So in the next step, actually we will define the touching point between tangent DA and the circle as point O, and here we have radius QO that is drawn to the point of tangency, that is to say to point O. Therefore the tangent DA is perpendicular to this radius, that is to say this angle equals to 90 degrees, and this angle also equals to 90 degrees. Okay? And we also know that all four angles of a square are right angles, so this angle ADC, is a right angle, it equals to 90 degrees. And we will define the touching point between tangent DC and this big circle as point F, and we will join together points F and Q by a straight line. Actually QF, line segment QF, is the radius of this big circle because of the fact that line segment QF starts from the center of this big circle, that is to say from point Q, and ends at point F, that is a point on the circle itself. Therefore QF is the radius of this big circle, that is to say it equals to 2R. And again we have this radius that is drawn to the point of tangency, that is to say point F. Therefore, according to rule number 1, the tangent DC is perpendicular to this radius, that is to say this angle is a right angle, it equals to 90 degrees, and this angle is also a right angle that equals to 90 degrees. And again, we will repeat on the same process as we did on this quadrilateral PLMB. So we will focus on quadrilateral DFOQ. So in quadrilateral DFOQ, again, in quadrilateral DFOQ, we have three right angles, 1, 2, and 3, and the sum of three right angles is equal to 270 degrees. And if we define this angle as angle Z, we know that the total sum of those four angles must be equal to 360 degrees, according to the rule that I stated, that the sum of the angles in any quadrilateral equals to 360 degrees. So we have the equality that 270 degrees plus angle Z equals to 360 degrees. We will subtract from this equality 270 degrees, and we will get that angle Z equals to 360 degrees minus 270 degrees is 90 degrees. So we found out that the size of angle Z is 90 degrees. It is a right angle. So we write that this angle is a right angle. It equals to 90 degrees. Again, it is exactly the same process as we did in this quadrilateral. So because of the fact that quadrilateral DFOQ has four right angles, it must be at least rectangle. So I write it down that quadrilateral DFOQ quadrilateral DFOQ must be at least a rectangle. If not square, it must be at least a rectangle because of the fact that it has four right angles. So it must be at least a rectangle. So if we assume that quadrilateral DFOQ is a rectangle, then we know that the opposite sides of a rectangle are equal to each other. And even if quadrilateral DFOQ is a square, then let alone that the opposite sides of a square are equal to each other. Of course, actually all the sides of a rectangle are equal to each other, so it doesn't matter at all if quadrilateral DFOQ is a rectangle or a square, because anyway the opposite sides of quadrilateral DFOQ will be equal to each other. So if we assume that quadrilateral DFOQ is a rectangle, then we know that the opposite sides of a rectangle are equal to each other. So DO equals to FQ. According to this rule, the opposite sides of a rectangle are equal to each other. The O equals to OQ. What we know, the O equals to FQ. The O equals to FQ. The O equals to FQ. But we know that FQ equals to 2R. So for this equality, we will conclude that the O also equals to 2R. The O also equals to 2R. DO equals to 2R. And we also know that the opposite sides OQ and DA also equal to each other. OQ equals to DF, according to the rule that the opposite sides of a rectangle are equal to each other. The opposite side OQ equals to the opposite side DA. But we know that OQ equals to 2R. So from this equality we will conclude that DF also equals to 2R. DF also equals to 2R. So we'll write here that DF equals to 2R. So as you can see, quadrilateral DFOQ is not a rectangle but a square. Okay, because all of its sides are equal to each other, it equals to 2R. So quadrilateral DFOQ is a square. We will calculate the size of side of line segment OA. So OA, as you can see from the drawing, OA, this line segment equals to DA minus DO. DA minus DO. I will repeat again. OA equals to DA minus DO. Okay, so OA equals to DA, that is 8 units, minus DO, that equals to 2R. So in total, we found out that OA equals to 8 minus 2R. Okay, OA equals to 8 minus 2R. So we write here that OA equals to 8 minus 2R. Okay. In the next step, we will join together points Q and A by a straight line. We will define the touching point between tangent AE to this big circle as point G, and we will join together points Q and G by a straight line. Again, actually QG is the radius of this big circle because of the fact that it starts from the center of the circle, that is to say from point Q, and ends at point G, that is a point on the circle itself. Therefore QG is defined as the radius of this big circle, that is to say it equals to 2R. And we have also rule number 1 that states that if the radius QG is drawn to the point of tangency, that is to say to point G, as you can see, indeed the radius QG, this radius that equals to 2R, is indeed drawn to the point of tangency, that is to say to point G. Therefore, according to rule number 1, the tangent AE is perpendicular to this radius, that is to say this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in the next step, we will prove that the right triangle AGQ is congruent to the right triangle AOQ. Okay, so we will focus on the right triangles triangle AQG, and the right triangle, triangle AQA, AQO, the right triangle AQO. And we will prove, I'll repeat again, we will prove that the right triangle AQG is congruent to the right triangle AQO. Okay? First of all, we know that AG equals to AO, AG equals to AO according to rule number 2. AG equals to AO according to rule number 2. Rule number 2 states that if from external point, that is to say point A, we have two tangents to this big circle, tangent AG and tangent AO. So because of the fact that we have two tangents from an external point to this big circle, then the lengths of those two tangents will be equal to each other. That is to say, AG equals to AO according to rule number 2. And we also know that QG equals to OQ equals to 2R equals to the radius of the big circle. QG equals to QO equals to the radius of the big circle, that is 2R. Okay, QG equals to QO equals to the radius of the big circle, that is 2R. And QA is a common side, it belongs to both triangles, so we can write down that QA equals to QA as a common side that belongs to both triangles. So we actually proved that three sides of the right triangle AQG are correspondingly equal to the three sides of the right triangle AQO. Therefore, we actually proved that the right triangle AQG congruent to the right triangle AQO according to side rule. Okay, I'm writing down the right triangle AQG is congruent. I remind you again that this sign is a sign of congruent to the right triangle AQO according to side rule. And from the fact that those two right triangles congruent to each other, we will conclude that angle QAG, this angle, is equal to angle OAQ, this angle. So those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore those two corresponding angles will be equal to each other. So we will write down that angle QAG is equal to angle QAO. Angle QAO and if we define this angle as beta, then this angle, angle QAO, will be also equal to beta because of the fact that those two angles are equal to each other. So we found out that angle QAG equals to angle QAO equals to beta according to our definition. Okay. I'll repeat again that all four angles of a square are right angles. So this angle DAB is a right angle. It equals to 90 degrees because it is one of the square's angle, one of the square angles, that it must be a right angle. So angle DAB equals to 90 degrees. But angle DAB consists of four angles, alpha, alpha, beta, and beta. So angle DAB equals to 2 alpha plus 2 beta. Angle DAB equals to 2 alpha plus 2 beta. So from this equality we will conclude that 2 alpha plus 2 beta equals to 90 degrees. This will be equation number 1. 2 alpha plus 2 beta equals to 90 degrees. Here we will divide equation number 1 by 2 and we will get that alpha plus beta equals to 90 degrees over 2 is 45 degrees. But if alpha plus beta equals to 45 degrees, then tangent alpha plus beta will be equal to tangent 45 degrees. Very simple. Okay, if alpha plus beta equals to 45 degrees, then tangent alpha plus beta equals to tangent 45 degrees. Okay, but tangent 45 degrees equals to 1. So we write down that tangent alpha plus beta equals to 1. This is equation number 1. Tangent alpha plus beta equals to 1. But actually we have trigonometric identity for the value of tangent alpha plus beta. According to the following trigonometric identity, the value of tangent alpha plus beta is actually tangent alpha plus tangent beta over 1 minus tangent alpha times tangent beta. So tangent alpha plus beta equals to tangent alpha plus tangent beta over 1 minus tangent alpha times tangent beta. So according to this trigonometric identity, we can substitute tangent alpha plus beta in equation number 1 by this expression, because this expression equals to tangent alpha plus beta. So we'll do it now. So equation number 1 will be that instead tangent alpha plus beta, we will write down this expression. Tangent alpha plus tangent beta over 1 minus tangent alpha times tangent beta. All equals to 1. According to equation number 1, this expression equals to 1. This is actually tangent alpha plus beta. So we got this equation after we substituted tangent alpha plus beta by this expression. So in the next step, we will find out the values of tangent alpha and tangent beta, and we will substitute tangent alpha and tangent beta in equation number 1 by the values for tangent alpha and tangent beta that we will find out from the drawing. Okay, so what is the value of tangent alpha? From the drawing we can see that the value of tangent alpha, if we focus on the right triangle APM, this right triangle. In the right triangle, triangle APM, tangent alpha equals to PM over AM. PM over AM. Again, triangle alpha in the right triangle APM, triangle alpha equals to PM over AM. But what is the value of PM? PM equals to R, and AM equals to 8 minus R. This is 8 minus R. So AM equals to 8 minus R. We found out that tangent alpha equals to R over 8 minus R. I'll repeat again. We found out that tangent alpha equals to R over 8 minus R. And what is the value of tangent beta? If you focus on the right triangle, triangle AQO, so if you focus on the right triangle AQO, tangent beta equals to QO over OA. Again, tangent beta equals to QO over OA, but we know that QO equals to 2R and OA equals to 8 minus 2R. So in total we got that tangent beta equals to 2R over 8 minus 2R. Again, we found out the value of tangent beta equals to 2R over 8 minus R, and tangent alpha equals to R over 8 minus R. So now we can substitute the values, we can substitute tangent alpha and tangent beta in equation number 1 by the values that we found here. Okay, so we will do it now. So in equation number 1, instead of tangent alpha, we will write down R over 8 minus R plus tangent beta equals to 2R over 8 minus 2R, all divided by 1 minus tangent alpha times tangent beta. Tangent alpha is R over 8 minus R, and tangent beta is 2R over 8 minus 2R, and all equals to 1. Okay, so we actually got this equation number 1 after we substituted tangent alpha and tangent beta in this equation number 1 by the values that we found for tangent alpha and tangent beta. So we have here one equation with one variable that is R, the radius of the small circle. We will do a common factor for these two expressions, and we will take out a common factor for 1 and those this expression, and actually if we focus on the numerator, the common factor will be 8 minus R times 8 minus 2R, and in the numerator we will have R when we have to multiply R by 8 minus 2R in order to get this expression, and we also have 2R, and we have to multiply 2R by 8 minus r in order to get this expression. So actually this expression is exactly equal to this expression, and then we will divide all, and here we will substitute 1 by 8 minus r over 8 minus r, it equals to 1 of course, and we will multiply it by 8 minus 2r over 8 minus 2r, that is also equals to r. So in total this expression equals to 1, and then we will subtract from 1 r times 2r, that is actually 2 minus 2r squared minus r times minus r times 2r is minus 2r squared. So actually we have here 8 minus r times 8 minus 2r, and we have here 8 minus 2r times 8 minus 2r, so those expressions will be cancelled by this expression, and what is left after we cancel those two expressions, what is left is actually r times 8 minus r times 8 minus 2r plus 2r times 8 minus r, all divided by 8 minus r times 8 minus 2r minus 2r squared, all equals to 1. So actually this is what is left after we cancel those two expressions. Here we will cross multiply equation number 1, and we will get that r times 8 minus 2r plus 2r times 8 minus r equals to 8 minus r times 8 minus 2r minus 2r squared. So here we will open the brackets on both sides of the equation number 1, and we will get that r times 8 is 8r, r times minus 2r is minus 2r squared, plus 2r times 8 is 16r, 2r minus times minus r is minus 2r squared, all equals to 8 times 8 is 64, 8 times minus 2r is minus 16r, minus r times 8 is minus 8r, and minus r times minus 2r is plus 2r squared minus 2r squared. So actually here plus 2r squared minus 2r squared is 0, so it will be cancelled, and what is left after we cancelled this expression is, here we have 2r plus 16r is 24r, minus 2r squared is minus 4r squared, all equals to 64 minus 16r minus 8r is minus 24r. Okay, So here we will subtract 24r from equation number 1, and we will get that minus 4r squared equals to here we have minus 24 square minus 24 square minus 24 square is minus 48 r minus 48 r minus 48 r is minus 24 r minus 24 r is minus 48 r plus 64. So here we will add to equation number 1 44 r squared. We will get that 4r squared minus 48r plus 64 equals to 0. So here we will divide this quadratic equation by 4, and we will get that r squared minus 12r plus 16 equals to 0. So we got this quadratic equation, and we know that the general formula for a quadratic equation is ax squared plus bx plus c equals to 0 when a, b, and c in this general formula for quadratic equation are the coefficients of this quadratic equation, and x is the variable that we are looking for, and we will find out the value of x according to a special formula for x. The special formula for x is x equals to minus b plus minus root of b squared minus 4 times a times c over 2 times a. Okay, when a, b, and c in this formula are the coefficients of this quadratic equation, and x is the variable that we are looking for. In our specific quadratic equation, x equals to r, the variable is r. The variable that we are looking for is r. So x equals to r. The coefficient a equals to 1. The coefficient b equals to minus 12. And the coefficient c in our specific quadratic equation equals to 16. So now we will put this data inside the equation for x in order to find out the value of r. So we know that x equals to r, so x equals to r, so we have r that equals to minus b, b equals to minus 12, and minus 12 is 12, plus minus root of b squared, b equals to minus 12, and minus 12 squared is 144, minus 4 times a is 1, minus 4 times 1 is minus 4, and minus 4 times 16 is minus 64, over 2a, 2a is 2 because 2 times 1 is 2, and so the radius of the small circle equals to 12 plus minus 144 minus 64 is 80 over 2. So we got this expression for the radius of the small circle. Actually 80 is 4 times 20, so I write it down. So R equals to 12 plus minus. Instead of 80, we will write down 4 times 20 over 2. So actually, the square root of 4 is 2. So R equals to 12 plus minus. Again, the root of 4 is 2. Inside the root, we only left with 20, all divided by 2. And so R actually equals to 12 over 2 is 6, and 2 over 2 is 1. So it is 6 plus minus, and 20 is 4 times 5. So inside the root, we will have 4 times 5. And the root of 4 is 2. So we got that the radius of the small circle equals to 6 plus minus. The root of 4 is 2 again. 2, and inside the root we have only 5. We left only with 5. So we have here two possibilities for R, two roots for R. The first solution is that R equals to 6 plus 2 times root 5. And the second solution to the quadratic equation is that R equals to 6 minus 2 times root 5. Okay, so we got those two solutions to the quadratic equation. And as you can see from the drawing, the radius, one side of this square equals to 8 units, and we have the small circle and also the big circle. They are located inside the square. Okay, so the radius of the small circle must be less than 8 units in order that the circle will be located inside this square. Otherwise, if the radius of the small circle is bigger than 8 units, then the small circle will not be located totally inside the square. Therefore, the radius must be less than 8 units. So R must be less than 8 units, and this answer that R equals to 6 plus 2 times root 5 gives us result that R is greater than 8 units. This answer is incorrect answer because R must be less than 8 units. So we left only with the answer that R equals to 6 minus 2 times root 5 units. Or in terms of numbers, it equals to 1.53 units. So the answer to the question is that the radius of this small circle equals either to 6 minus 2 times root 5 units, or in terms of numbers, the radius of this small circle equals to 1.53 units, okay? So now I will summarize the lecture. Actually, we wanted to find out the radius of this small circle. We have square ABCD, and those two circles are located inside this square. We know that one side of square ABCD equals to 8 units, and we know that the radius of this big circle equals to 2r, while the radius of this small circle equals to r, and we want to find out the value of r, or the size of the radius of this small circle. Okay, actually before we started to solve this question, I presented to you two new rules. The first rule is that a tangent to a circle is perpendicular to the radius drawn to its point of tangency. Okay? I'll read rule number one again. A tangent to a circle is perpendicular to the radius drawn to its point of tangency. So what is the meaning of rule number one? Rule number one states that whenever the radius of a circle is drawn to the point of tangency, that is to say point M, then the tangent AB will be perpendicular to this radius. That is to say this angle is 90 degrees and this angle is also 90 degrees. Okay? So if you have a radius that is drawn to the point of tangency, then the angle between the tangent and that radius will be equal to 90 degrees. It will be a right angle. That is rule number one, and we also have rule number two. Rule number two states that if from one external point two tangents are drawn to a circle, then they have equal lengths. So what is the meaning of rule number two? The meaning of rule number two, that if we have external point of this circle, P is external point in relation to this circle because it is not located inside this circle nor on the circle. It is located outside of this circle, therefore it is defined as external point. So if from any external point we will draw two tangents to a circle, then the lengths of those two tangents will be equal to each other. That is to say PA equals to PB. Okay, so whenever you draw from an external point of a circle two tangents to the circle, then the lengths of those two circles will be equal to each other. In this case, PA equals to PB because P is an external point, and from the external point P we draw two tangents to this circle, therefore the lengths of those two tangents will be equal to each other. That is to say PA equals to PB. Okay, that is rule number two. Then we actually defined the center of the small circle as point P and the center of the big circle is point Q. We join together points P and A by a straight line, and we join together points P and M by a straight line. Actually, AB is tangent to the circle at point M, and we have this radius that is drawn to the point of tangency, that is to say to point M. Therefore, according to rule number one, the tangent AB is perpendicular to this radius, that is to say this angle is 90 degrees and this angle is 90 degrees also. And the same thing is about this radius. We have the tangent AE, this is perpendicular, and the tangent AB, the touching point between tangent AB to this small circle is at point N. Then we connect together points P and N by a straight line. So Pn is the radius of this circle because of the fact that it starts from the center of this circle, that is to say from point P, and ends at point N, that is a point on the small circle itself. Therefore, Pn is the radius of this circle, and this radius Pn is drawn to the point of tendency, that is to say to point N. Therefore, according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Okay? So, the same rule we have also here. We have this radius that is drawn to the point of tangency, that is to say to point L. Therefore, according to rule number 1, the tangent BC is perpendicular to this radius, that is to say this angle is 90 degrees and this angle is also 90 degrees. Okay? So actually, and we know that all four angles of a square are right angles, they are equal to 90 degrees, and especially this angle equals to 90 degrees. So here, if we focus on quadrilateral PLMB, it has three right angles. The sum of three right angles is 270 degrees. And we know that the sum of the angles in any quadrilateral equals to 360 degrees. That is to say 270 degrees plus the size of this angle that we defined as angle Z must be equal to 360 degrees. Okay? So we actually subtracted 270 degrees from the equality, and we got that the size of this angle, angle Z, is 90 degrees. That is to say, in quadrilateral PLMB, we have four right angles, and in any quadrilateral that has four right angles, it must be at least left angle, if not a square. And we know that opposite sides of a rectangle are equal to each other, so MB equals to PL. But we know that PL equals to R, so MB will be also equal to R. And we also know that the opposite sides PM and LB are equal to each other, but we know that PL equals to R, therefore LB will be also equal to R because of the fact that PM equals to LB. So we got that, and we found out that the quadrilateral PLMB is a square. Okay? And then we proved that those two right triangles can go into each other according to side rule. Why? Because we have side AM of triangle APM is equal to side AG to side AN of triangle APN according to rule number 2, because of the fact that if from external point A we draw two tangents to this small circle, they will be equal in their lengths. That is to say, AM equals to AN according to rule number 2, and also PM equals to PN equals to the radius of this small circle. And we also have a common side, AP equals to AP is a common side. So we actually proved that all the three sides of this right triangle correspond equal to all the three sides of this right triangle. Therefore, we proved that those two right triangles can go into each other according to side rule. So, from the fact that those two triangles can go into each other, we will conclude that those two angles are equal to each other. Because of the fact that, according to the rule, that corresponding angles in congruent triangles are equal to each other. And if this angle is alpha, this angle will be also equal to alpha. Okay? Then we have here this radius that is drawn to the point of tangency. Therefore, according to rule number 1, the tangent AD is perpendicular to this radius OQ, that is to say this angle is 90 degrees and this angle is also 90 degrees. And we know that all the sides, all the angles of a square are right angles, therefore this is a right angle that equals to 90 degrees. We joined points Q and E by a straight line. QE is the radius of this big circle, because of the fact that line segment QE starts from the center of this big circle, that is to say from point Q, and ends at point F, that is a point on the circle itself. Therefore, QF is the radius of this big circle, that is to say it equals to 2r. And actually this radius is drawn to the point of tangency, that is to say it is drawn to point F, that is the point of tangency. Therefore, according to rule number 1, the tangent DC is perpendicular to this radius, that is to say this angle is 90 degrees and this angle is also 90 degrees. So we actually got that in quadrilateral DFOQ, this quadrilateral, we have 3 right angles, 1, 2 and 3. And we know that the sum of the angles in any quadrilateral equals to 360 degrees. Therefore, the sum of those 4 angles must be equal to 360 degrees. So here we have 3 angles that the sum of them is 270 degrees, plus the 4th angle that is defined as angle Z must be equal to 360 degrees. So we got the equality that 270 degrees plus angle Z equals to 360 degrees. Then we subtracted from the equality 270 degrees, and we got that angle Z equals to 90 degrees. So we got that the quadrilateral DFOQ has 4 right angles, therefore it must be at least a rectangle if not a square. And we know that the opposite sides of a rectangle are equal to each other, that is to say OQ equals to DF. But we know that OQ equals to 2R, therefore DF will be also equal to 2R. And we also, according to the rule that the opposite sides of a rectangle are equal to each other, QF will be equal to DO, but we know that QF equals to 2R, then therefore DO will be also equal to 2R. So we found out that quadrilateral DFOQ is not a rectangle but a square. Okay, and then we calculated the value of OA. Actually OA equals to DA minus DO, that is to say OA equals to DA, that is 8 units, minus DO, that is 2R. So in total we got that OA equals to 8 minus 2R, and we actually also found out the size of line segment AM. The size of line segment AM equals to AB minus MB. AB equals to 8 units and MB equals to R, so the size of AM is AB, that is 8, minus MB, that is R, or the size of AM is 8 minus R. Okay? And I'll repeat again. After we found out that we actually proved that those 2 right angles congruent to each other according to side rule. Why they congruent to each other? Because we have side AG that equals to side OA according to rule number 2, because from external point A we draw 2 tangents to this big circle. Therefore, according to rule number 2, the lengths of those 2 tangents are equal to each other, that is to say AG equals to AO, and we also know that QG equals to QO equals to the radius of this big circle. And we also have a common side. QA is a common side that belongs to both triangles, so QA equals to QA. So we proved that those 2 right triangles can go into each other according to side rule, and from the fact that those 2 triangles can go into each other, we concluded that those 2 angles are equal to each other. And according to the rule that corresponding angles in congruent triangles are equal to each other, and if this angle is beta, this angle will be also equal to beta because of the fact that they are equal to each other. So we got that actually angle BAD equals to 2 alpha plus 2 beta, but angle BAD is actually also equals to 90 degrees because it is 1 out of 4 angles of square ABCD, and we know that all the 4 angles of square ABCD are right angles, and especially angle DAB equals to 90 degrees. So from one side, angle DAB equals to 90 degrees, and from the other side, angle DAB equals to 2 alpha plus 2 beta. So we found out that that 2 alpha plus 2 beta equals to 90 degrees. We divided the equality by 2, and we got that alpha plus beta equals to 45 degrees. But if alpha plus beta equals to 45 degrees, then tangent alpha plus beta equals to tangent 45 degrees. And tangent 45 degrees is 1. So we got that tangent alpha plus beta equals to 1. And we have trigonometric identity for tangent alpha plus beta. Actually, tangent alpha plus beta equals to tangent alpha plus tangent beta minus 1 over tangent alpha times tangent beta. And we have this trigonometric identity. So we substituted tangent alpha plus beta in equation number 1 by this expression, and we got this expression. And then we calculated the value of tangent alpha and tangent beta, and we substituted tangent alpha and tangent beta in equation number 1 by the values that we found for tangent alpha and tangent beta. And we actually found out that the value of tangent alpha, if we focus on triangle APM, equals to R minus 8 minus R. Tangent alpha equals to R over 8 minus R, and tangent beta, if we focus on these right angles, equals to 2R over 8 minus 2R. Okay? So, and we substitute the tangent alpha and tangent beta by the values that I mentioned here, with those two values. After we substitute the tangent alpha and tangent beta in equation number 1 by those values, we got this equation number 1. We solved this equation, we got a quadratic equation, and we got two solutions to the quadratic equation. The first solution was that the radius of the small circle equals to 6 plus 2 times root 5, and the second solution was that the radius of the small circle equals to 6 minus 2 times root 5. So here we can see from the drawing that the size of one side of square ABCD is 8 units. So, and the small circle is located inside the square. Therefore, the radius of the small circle must be less than 8 units in order to be located inside this square. Therefore, the possibility that the radius of this small circle is greater than 8 units is not correct, because the radius must be less than 8 units. So the only option that we have, that the radius of the small circle equals to 6 minus 2 times root 5 units, or in terms of numbers is 1.53 units. Again, the radius of this small circle equals to either 6 minus 2 times root 5 units, or in terms of numbers, the radius of this small circle equals to 1.53 units. Okay, thank you very much.